I just gave you the what do you mean? You have more notes than you need, more slides than you need.
I was trying to read the rule.
Oh, yes, the rule. Okay, what language does that look like?
French.
It is French. Mr. L'Hôpital was a French mathematician. All right, the rule was named after him, but as with a lot of things that happened in math, he wasn't the first one to discover it. He was just the first person to publish it. All right, so he took something, so we saw that with Leibniz and Newton, that Leibniz worked on the derivative first but failed to publish. Newton published, and so the world remembers Newton. And then same thing with this. All right, it was an Italian named Guillaume Bernoulli who came up with this. He just didn't publish anything. He wrote it down, he just didn't send it to the printer and get it published with his name on it. So to L'Hôpital's credit, he did say in his work, like, I got this from Bernoulli, but everybody still called it L'Hôpital because it was in L'Hôpital's book. So anyway, that's where it came from. All right, it looks like the hospital, but it's not. There's no S in there. It's L'Hôpital. The low is kind of... All right. Mr. L'Hôpital and Mr. Bernoulli, they dug into indeterminate forms. All right, so remember our indeterminate forms, 0 over 0 and infinity over infinity. Now you may be thinking, well, why didn't you teach us this when we were doing indeterminate forms back when we were doing chapter 1 and we were doing limits? It's because you also had to know derivatives. So I'm cycling back to indeterminate forms now that you know all the derivatives that there are. Okay, so you weren't equipped yet. You didn't have the skills to be able to do it. You had the intelligence, just not the skills. Now you have the skills and the intelligence to do both. All right, so here we go. Let's quick review what it means to divide two things. If you start with 0 on the top and you divide it by any number on the bottom, plus or minus, what do you get?
0.
Correct. As long as k is not what number?
0.
0. Okay, so it has to be a positive or a negative, k, not 0. All right, what if you start with any positive or negative on the top and you divide by 0? Then what do you get? What kind of infinity? Plus or minus infinity. Okay, it's because infinity has two sides. It has a positive side and it has a negative side. So what if you take 0 and divide it by 0? That was the classic indeterminate form that we learned about in chapter 1. Okay, so conversely, if you start with infinity on the top and you divide it by any positive or negative number, so infinity divided by anything, what do you get?
Infinity.
You still have infinity. If you take any positive or negative number and divide it by the largest number known to mankind that we can not even really get our minds around, then what do we get?
0.
We get 0 plus or minus. We get one side of 0 or the other. We never get 0 exactly, but we end up really close to 0 on one side or the other. And if we take infinity and we divide it by itself, then we have one of those classic indeterminate forms. Okay. It's when you encounter, yes, Catherine?
For infinity over plus or minus k, so the infinity in the numerator doesn't change from the plus or minus in the denominator?
Yeah, so we should be careful about that depending on what kind of, if you've got two negatives, it'll end up to be a positive. If you have one of each, it'll end up to be a negative. Okay, thanks.
Divided by 0.
Oh,
The other way around.
that's another indeterminate form. Okay, but we're only going to focus on the ones that are the same as each other for now. Okay? All right. One limit you have previously learned that was already indeterminate was the limit of sine of a over x over a over x as x approached 0. And what happened is when we plugged 0 directly in, we got sine of 0x over 0a, not 0x, 0a, and then over 0a. We know that that was sine of 0 over 0. And sine of 0 is 0. We knew that to be indeterminate form. But by the graph, we knew that we could figure out an answer. Okay, this was the graph that started out wavy on the sides, and then what did it do in the middle? It peaked. All right, and where did it peak? Well, sometimes at 1, it peaked at A, whatever A was. If A happened to be 1, then it would peak. But was it a continuous function? Okay, had an open hole in it. Okay, so by graph, I told you, just believe me that this is peaking at A. Okay, well now we can prove why it does that and why you have the limit, because you need derivatives to be able to do that. Okay, so the next slide has that graph on there that we looked at. There is, go ahead and make an open circle right here. Okay, there is an open circle there, but the level of that open circle is A, both on the left and the right. Okay, so that was a really famous limit that we talked about, and I just told you, just hang on, you have to trust me that that is the value of A, but I'm going to show you why. All right, so mathematicians, they had a hunch, like from graphs and stuff, they're like, I think it looks like it should work out to be this way, so our hunch is going to be this, but they never could prove it until the derivative was invented or discovered. And once they got the derivative, then they could work on that problem of indeterminate forms. So the people who worked on it, nope, I'm spelling it wrong. Bernoulli. Okay, Bernoulli, Italy. Okay, John was his first name. And then Guillaume was his first name, which is the French version of William, L'Hôpital. I usually don't put the little, I don't even know what it's called, but that little hat on that, but he was from France. Okay, so Bernoulli worked on it first, L'Hôpital took his work and then published it, and everybody calls it L'Hôpital's rule. So those are the guys who worked on it. This is what they said. All right, if, or suppose that, the limit of f of x and the limit of g of x are both equal to what? 0. Okay, then if you stack them, f of x over g of x, okay, if you stack them, then what would you have? What would you have on the top? 0. And what would you have on the bottom? Okay, so classic indeterminate form. All right, Bernoulli and L'Hôpital proved that you could take it a step further by finding the derivative. We'll go ahead and find the derivative instead. And the limit can be proven using derivatives. So take the numerator of the derivative and take the denominator of the derivative, and you won't get 0 over 0 anymore. You'll have an actual value of your limit that you're looking for. Okay, this only works on quotients, 0 over 0, or infinity over infinity. It doesn't work for any other form. It has to be a quotient. It has to be in an indeterminate form, 0 over 0 and infinity over infinity. That's the if part. So let's try it. Okay, here was this famous one. We know that according to what we've learned before, that the sine of x over x should have a limit value that's going to be equal to a, and in this case, a is what? 1. Okay, so we're going to say, all right, by substitution, I get the sine of 0 over 0, which is 0 over 0. That legitimizes the use of L'Hôpital's rule. You have to show that a substitution would produce an indeterminate form. And once the substitution produces an indeterminate form, then you can go to the next step and you can apply, and for abbreviated purposes, I'm just going to say LH for now. Okay, that's L'Hôpital. And L'Hôpital's rule says take the derivative. Okay, so what is the derivative of the numerator? It's not quotient rule. Hear me, okay? This is not quotient rule. Just because it's a quotient doesn't mean we're using the quotient rule. This is L'Hôpital's rule, which is applied only in indeterminate form situations. All you do is take the straight derivative of the numerator, which is what? Cosine x. And the straight derivative of the denominator, 1. And then try plugging into that. And you get cosine of 0 over 1. And what is the cosine of 0?
1.
And the answer was 1. And we knew it was going to be 1 because our graph, and I had told you before it was going to be 1. Okay, because that's the peak of where this happens. This will always work when you encounter an indeterminate form. Okay, so let's try this again. But part of the process is you have to show me that an indeterminate form makes L'Hopital's rule necessary. Don't just jump right into L'Hopital's rule for every single problem. It only works if there was an indeterminate form. So always check your substitution. All right, we're going to do the limit of this function. So we're going to plug in 0. So that would give me 4 plus 0 minus 2 over 0. Of course, the square root of 4 plus 0 is just the square root of 4. Which is 2 minus 2, which is 0 over 0. So once I've proven, yeah?
Why are we not saying 2 minus 2 minus 2?
Okay, that is a good question. Okay, because we proved this to be indeterminate, we can now apply L'Hopital, which goes back to a limit. Okay, and then we take the derivative. All right, what is the derivative of rad 4 plus x minus 2? How do I take the derivative of that? 1/2.
Parentheses.
4 plus x to the negative 1/2 times the chain rule, 1. Okay, minus technically, what is the derivative of 2? 0. And what is the derivative of the denominator? 1. Okay, I can clean this up. So what's left in the numerator? 1. What moves to the denominator? The 2 and?
4 plus x quantity.
Right. Right. And then I'll plug 0 into that. And so by plugging 0 into that, I'll get 1 over 2 rad 4 plus 0, which is 1 over 2 times 2, which is 1/4. So the answer to the limit is 1/4. Okay? Okay so far? All right, L'Hopital's rule the second. Okay, suppose that you do L'Hopital's rule the first, because what made it possible to do L'Hopital's rule? It was indeterminate. So suppose you do L'Hopital's rule and your answer is still indeterminate. Then you do it again. And then you do it again. And you just keep doing it until it's not going to be indeterminate anymore. And eventually, you'll run out of derivatives, right? Because, you know, if you have an x cubed, how many derivatives can you take? Eventually, you're going to run out. And at some point, you will run out. Okay? So you can do this n number of times. You're allowed an unlimited number of times. Okay? This is called a reiteration. That just means you repeat the process until you don't get indeterminate anymore. But again, note, this only works on quotients. And it has to work on 0 over 0 or infinity over infinity. Those are the only two. Okay, so let's try this. Always direct substitute first. So when I direct substitute, I'm going to get 0 minus the sign of 0 over 0 cubed, which is 0 over 0. So I got indeterminate the first time. So I'm going to apply L'Hopital back to a limit. And now I'll take the derivative. Okay. All right, Sydney, numerator derivative?
1
Uh-huh.
minus cosine x.
Okay, 1 minus cosine x, denominator derivative?
3x.
3x squared. Okay, we're going to plug 0 into that. That'll be 1 minus the cosine of 0 over 3 times 0 squared. All right, what's the cosine of 0? No, the cosine of 0 is not 0. The cosine of 0 is a different number. Cosine of 0 is 1, so I get 1 minus 1 over 0, which is 0 over 0 again. So I'll apply it again. And the power of this is you can just do it until you don't have an indeterminate form anymore. Okay, back to the limit. The derivative of 1 minus cosine. Well, the derivative of 1 is 0. What about the derivative of minus cosine? Positive. Yes, and it's because it's a minus, then it'll be back to a positive. And then what's the denominator? 6x. Plug 0 into that. Sine of 0 over 6 times 0. What's that going to be? All right, we're almost done because can you see what's going to happen to the denominator finally? What's the denominator? Okay, what's going to perpetually happen to the numerator?
Go back and forth.
Going to be back and forth. Sine, cosine. Okay, that's going to oscillate back and forth. But the denominator is eventually going to settle down. Okay?
Okay.
So there is an end in sight. All right, so last one. The derivative of sine is cosine. The derivative of 6x is 6. I'll plug 0 into that. And since the cosine of 0 is 1, then the value of this limit is 1/6. Okay, so it's a powerful rule that can be used. Yeah?
Do we have to write and apply?
No, I'm just doing that for our notes as we're learning. Usually do the first time maybe to let whoever's grading your paper know this is what you're doing. Kaylin, do you have a question?
No.
Okay.
What was the graph like?
The graph of the original,
Yeah.
it's gonna be discontinuous at 0. I don't know this one. I can't remember if it has a hole or if it's. It probably has a hole. It's got a hole at 0, 1/6.
But then how is it approaching? Is it just a flat line approaching?
No, it's probably oscillating and oscillating, and then eventually they're both approaching that value. You can take a look at it.
Why does this work? Because you're finding the derivative of.
Because you're finding continual slopes. And these things, well, they're eventually, because they're approaching an open hole, they're going to have the same slope. And eventually that
It's
okay.
like a proof. Okay. But that.
Okay, what's the mistake here? All right, so this is a good FRQ kind of question where they throw one up to you and they're like, find the mistake in what the student did. Okay, so let's start at the beginning. What should the student do?
Plug in 0.
Plug in 0, all right? So if the student plugged in 0, what would we get? 1 minus cosine of 0 over 0 plus 0 squared. What will that turn out to be?
0.
Okay. All right, so then the student proceeds. Okay, so did they take derivatives correctly?
Yeah.
Does it look like it? Okay. All right, so then we'll check 0 here. Sine of 0 over 1 plus 2 times 0. What do we get there? 0 over 1.
Let's just do
It's no longer indeterminate. This is what's 0 divided by anything, as long as it's not 0. And so the problem should have stopped there. Okay, but this person was really excited to keep going and keep going and keep going, and then eventually ended up with a false answer, even though their work kind of looks good. But they're failing to check and show that indeterminate form was actually required each time. Okay. Oh yeah, that I gave you a place to find that. This one was 0 over 0. This one is 0 over 1. Not indeterminate.
For a question like that,
Mhm.
would you be writing what they did wrong, or would you just be showing that?
It depends on if they say explain or justify your answer, then it would be a complete sentence. Sometimes they'll say show the corrected work. Okay. Now here's one that's going to be infinity over infinity. Okay, always plug in. So this time I'm plugging in pi. So the cosecant of pi over 1 plus the cotangent of pi. So you got to know your unit circle a little bit here. Okay, the cosecant of pi is infinity. The cotangent of pi is also infinity. And what happens when you add 1 to infinity?
It just
Stays infinity. And so we have an indeterminate form. L'Hopital works on this as well. All right, so apply the L'Hopital's rule. Back to a limit anytime you apply it. And this time it's x approaching pi. All right, what's the derivative of cosecant? Negative cosecant x, cotangent x. Okay, and then the derivative of 1 plus cotangent.
0 plus.
Okay, negative cosecant squared. Okay, you have to reduce at this point. This is reducible. Why?
The cosecant.
Okay, the cosecant, there's one cosecant on the top, and there's basically two cosecants on the bottom. So I do need to, if you don't reduce, then you're going to end up stuck in a never-ending cycle. So this would be negative cotangent of x over negative cos. Yeah, so we're going to want to reduce the negatives as well. Is there anything else we can reduce?
Yeah.
Okay. All right, what is cotangent?
Cosine over sine.
Cosine over sine. What's cosecant? 1 over sine. If you don't reduce, you'll get stuck in a never-ending, so you do need to reduce this. So cotangent is cosine of x over sine of x. Cosecant is 1 over sine of x.
Multiply by sine.
Multiply by the reciprocal, yep. So multiply by, instead of 1 over sine of x, this is your trig here, sine of x over 1.
Oh, it's gross.
No, it's not. Why? Why gross?
It just becomes the limit of cosine.
Because what does the sine of x's do? Reduce. Okay, and our last thing is that we're left with the cosine of pi. And what is the cosine of pi? -1.